Hello and welcome back to machine learning. In this video, we are going to talk about model representation and interpretability, as well as bias and variance trade-offs. So let's begin. The goal of any supervised machine learning technique is to learn or to derive a target function which can best determine the target variable from the set of input variables, right? So it's first to learn or to be able to classify, to perform descriptive modeling or predictive modeling. And the key consideration in learning the target function from the training data is the extent of generalization. We know what generalization is from one of our previous videos. So the key concept or the goal of the whole machine learning process is to learn or derive a target function. And in deriving a target function or in learning, you can increase that by seeing the extent of generalization. So input data is just a limited and specific view, and the new unknown data may not be of the same form as the training data that you have used. So fitness of a target function is approximated by a learning algorithm. It determines how correctly it is able to classify a set of data it has never seen, right? So we measure accuracy not by the data that it has already seen, but by the data that it has not seen before. And when it comes to the fitness function, we can have three problems. The first problem is underfitting. So this is an example of a linear regression where there is underfitting. As you can see, there are only 2 points that are touching the line and all the other points are not touching the line. So this is an underfit. There can be a balanced fit where you can see most of the points touching the line, some points almost touching the line, and there's only one point that's a little bit far away. Overfitting is also a problem because as you can see here, there is a line created. Okay, it's a polynomial regression, but the line is so fitting so well to all the data points that it's definitely going to give me errors when it sees unknown data. So here, this is also a problem. If you are using SVM or some partitioning algorithm, underfit would mean that all these points are there are these 3 points or 4 points which should belong to the other class but are actually in this side of the line. A balanced fit would mean this one where there's only one point which is not inside the proper class, and an overfit would mean like this one where you are creating the partition which fits so well that every point is split like this. Now there can be a new point that appears in this position, okay? And this point is supposed to be a circle, so it should be falling into this class. But because your algorithm is so overfitted, it's going to put this in the other class, okay? So fitting can have all these problems. There can be underfitting, there can also be overfitting. Let's first talk about what underfitting is and how you can solve that. So if the target function is kept too simple, it may not be able to capture the essential nuances and represent your underlying data very well. And a typical case of underfitting can occur when you're trying to represent a non-linear data model with a linear model, right? So it's a model that cannot be represented with a straight line, and yet you are trying to fit everything on a straight line. And many times underfitting can happen due to unavailability of sufficient training data. So sometimes your data set is just too small to be able to predict anything. And underfitting can result in both poor performance with the training data as well as a poor generalization of the test data. How can you avoid underfitting? You can avoid it by using more training data, and you can avoid it by reducing the features by effective feature selection. So instead of taking all the columns, you could just use some of the columns for training. Let's now talk about overfitting. So overfitting refers to a situation where the model has been designed in such a way that it emulates the training data very, very closely. Okay, so your model is designed so well that it fits the training data completely. And in such a case, what happens? Any deviation from that training data, like if you have noise or outliers or anything, all that gets embedded into the model. Okay, so there can be, even in the training data, there can be incorrect values, there can be outliers, and all these also get embedded into your model. So it adversely affects the performance of your model when the test data comes in. Okay, and overfitting in many cases can occur as a result of trying to fit an excessively complex model to closely match the training data. So if you're just aiming for fitting the model completely on the training data, then overfitting can occur. And the target function in these cases will try to make sure that all the training data points are correctly partitioned by the decision boundary, as we saw in the diagram before. Okay, but most of the time what happens that this exact nature is not replicated in the unknown test data set. Okay, so your training data gets partitioned very well, but due to overfitting, the unknown test data set does not work well. So the target function results in a wrong classification in the test data set. And that's why it is called overfitting. And overfitting results in a good performance when you're training the data, of course, but when you are testing the data, you will have a poor performance because there is no generalization, okay? And how can you avoid overfitting? You can avoid overfitting by using some resampling techniques like k-fold cross-validation that we just learned. And you can also do a holdback of a validation data set. You could also remove some of the nodes which have very little or no predictive power. If you're doing, a decision tree or something, you could remove some of the nodes instead of keeping all the nodes. Both these techniques, which are overfitting and underfitting, both of them have poor classification quality. So if you have a lot of overfitting or a lot of underfitting, it will be shown in your classification accuracy because the classification accuracy will be very low. Now let's talk about the bias and the variance trade-off. So in supervised learning, the class value, which is assigned by the learning model, built on the basis of training data, may vary from the actual class value, right? We know that the machine learning model is definitely not 100% accurate. So whatever data, whatever prediction it is making might be different than whatever is the actual scenario. And this error can be of two types. There can be two types of errors in prediction. One is due to bias, another one is due to variance. So here there are some graphs displaying the same thing. So these two graphs in the bottom show low bias. So this is an example of low bias, and the graphs on the top, they are an example of high bias. Okay, so here this is an example of low bias and low variance. This is an example of low bias, high variance, as you can see. Okay, because what's happening there is in high variance, the data will be more dispersed. And here is an example of low variance and high bias. And here it's an example of high variance and high bias. Let's talk about errors that can occur because of bias. Errors due to bias arise from simplifying assumptions made by the model to make the target function less complicated or easier to learn. So when you're doing oversimplification or overgeneralization, then you will have bias. So due to underfitting of the model, right? We saw that earlier. Because of underfitting, you can have error due to bias. Parametric models generally have high bias, making them easier to understand or interpret and faster to learn. So most parametric models suffer from this problem. They also have poor performance on data sets, which are not complex in nature. So underfitting would result into high bias. Let's talk about errors due to variance. So sometimes errors can occur due to variance as well. Variance, which means your data is very much dispersed in the training data set. It means in your training set, which you are using, there's a lot of difference. And these training data sets, which are randomly sampled, are used to train your model. So the difference in data sets should not be very significant in the model because you're using the same data set, but sometimes it is very different. And this is the case that happens in overfitting. Okay. And since the model matches the training data, even if there is a small change in the training data, the model will get, that change will get magnified in the training of the model. Let's now talk about the bias and variance trade-off. So what can you let go of? On the one hand, if you have parametric algorithms, you will have high bias but low variance. But if you use non-parametric algorithms, you will have low bias but high variance. And the best solution is to have a model that has low bias as well as low variance. Okay, but that may not be possible in reality. So what do we do? The goal of supervised learning is to achieve a balance between bias and variance. We can never get 100% accuracy, but we can, try to be as close to it as possible. And the learning algorithm which is chosen and the user parameters which are chosen, which are configured, they can help to make this trade-off between bias and variance. Okay, you cannot have both of them low, but you can have them as low as possible. For example, you have a popular supervised algorithm, which is KNN, K nearest neighbor. And here you can select a value of K in such a way that you can make a trade-off between bias and variance. So select a K in such a way that the bias and variance are not affecting your algorithm performance much. Okay, so in one hand, when the value of K is decreased, the model becomes simpler to fit and the bias increases. So when the value of K is decreased, the model becomes simpler and bias increases. Okay, and if you increase the value of K, then the variance increases. So decreasing the value of K increases bias, increasing the value of K increases variance, and we want both to be low. So you pick a value of K in such a way that both are moderate, bias and variance. Let's take a look at how we can implement some of the splitting techniques that we saw. So first of all, the data set I'm using is the Auto MPG data set, which I've used several times in the previous videos. So we're just reading that and printing out the first 5 rows, as you can see here. And then we will see the different methods we can use to split this data. So if you notice here, the first step, as you can see, is the holdout method. So in the holdout method, you can just import the train test split module from your sklearn.model selection. And the data shape is currently this 398 and 9. That means there are 398 rows and 9 columns. And to split using the holdout method, you just have to do train test split, pass your data, pass the testing size. So I want 30% of data to be test data. The random state is 123, which just means that it's the seed value you are providing to the random function. And then you can see here, this function will return to me the training data and the testing data split. And if you check out the length, you will see training data is about 278 rows. Testing is 120 rows, which is our 70-30 split as we wanted. Okay, so this is how the holdout method works. It's very simple, it's very straightforward. Most of the time, this is the one people use. And the next method we saw was k-fold cross-validation, which looks like this. So in k-fold cross-validation, if you want to implement it, you have to import from sklearn.model selection the k-fold function and create an object of it. So you're creating k-fold, you're passing into it 10 splits. Okay, so what it basically does is it gives you indices from your for your data to split. Okay, and I want to perform 10-fold validation. So that's why I'm passing the value 10 for number of splits. And it will give me 10 different indices. Now, all I have to do is apply that, okay, apply kf.split onto my data. These numbers are generated at random, the 10 indices, and now I'm applying it on my data. Okay, so this will give me the train and test. So I will get 10 different train and test values for implementing. So now what I can do is I can um, sort of train my model 10 times. Okay, so if it is a 10 split thing, then this for loop will run 10 times and I can train a model 10 times and then use whatever is happening, and then I can use it to test. Okay, so this will definitely improve the accuracy because I'm training my model 10 times. The next method we saw was bootstrapping. So bootstrapping, remember, it takes a simple random sample, but with replacement instead of without replacement. So let's take a look at bootstrapping. So to perform bootstrapping, first of all, you have to get this from sklearn.utils. You need to get a resample. Sorry for that. Yeah. You need to get resample from sklearn.utils. And then you need to locate from there using the ilog function. You will get all the columns from 0 to 9 because our data contains that many columns, 9 columns. You'll get all of them into X, print X. So this is what X looks like, okay? All the 398 rows and 9 columns. Now to do the resampling, I want to generate a sample of size 200, okay, with partitions. I want to generate a sample of size 200 with partitions. To do that, you just have to call the resample function, pass into it your data, and pass how many samples you want. I want 200, and my random state is 0, which means that's the seed value for my random function to start generating the numbers. So I will get 200 samples, but there is a possibility that in these 200 samples, some rows will be repeating. For example, the third row, okay, which is about AMC Rebel SST, could be coming twice, okay, even though in my data it is only once. Row like a Ford Mustang can come 5 times, even though here it is only once, okay. This is happening because it is a simple random sample with replacement, which means I'm replacing it back and then picking the next row. So this is how the splitting techniques work, and I hope you understood this. I'll see you in the next video. Thank you for watching.